Hi everyone, here we are on chapter 20. Now chapter 20 is on acids and bases. So what we're first going to do is we are going to talk about acids first. Now there's a reason why the acids are in red, why I have it in red font here. If you have ever used litmus paper before, probably in elementary school or middle school, they're like these little thin strips of paper that you can dip into solutions and then they will turn color. So if the litmus paper turns red, then that's telling us that the solution is an acid or it is acidic. And then if the litmus paper turns blue, then that's telling us it's a base. So then acids are red, bases are blue. So it's easy to remember that bases are blue because they both begin with the letter B. All right, but first we're going to talk about acids. So if you remember, your formula for the acids is HX. Remember the H in the front? Okay, hydrogen in the front. So that's usually a pretty good indicator that it is an acid. So some of these characteristics of acids you are already familiar with. Your acids have a sour taste. So things that are acidic that you have experienced before, like lemons, let's see what else, oranges. So anything that is citric, because they contain citric acid, or like, your sour candies and stuff like that, those are all things that are acidic. When your acids are dissolved in water, so aqueous solutions, remember dissolved in water, they are electrolytes. So what do electrolytes do again? They conduct electricity. So when your acids are dissolved in water, they also will conduct electricity. And then we already talked about this, how they will turn the litmus paper red. And then some of your acids will react with metals to produce hydrogen gas. Okay? And this is something that you guys have seen before. If you remember the lab we did in first semester where you had to put your thumb on the tube and tilt the tube, invert the tube upside down, put your hand in water. Remember you saw the acid coming down and it was reacting with the magnesium like strip, and then eventually it formed all these bubbles and stuff. So that is what you saw in that lab with the acid reacting with the metal. And then right here, your acids will react with hydroxides. Remember, hydroxide is OH minus. It's a polyatomic ion to produce salt and water. So our generic equation for an acid-base reaction, we say acid plus base gives you salt and water. Okay, remember salt. Right here, salt. Salt is a generic term for ionic compound, okay? And so that is basically an overview on what acids are. Now let's talk about bases. All right, your bases. So here is your general formula for a base, okay? So let me circle that actually. All right, so the X is a metal, and then you can see then you have hydroxide combined with that metal. All right, your bases typically have a bitter taste and they feel slippery. So like your soaps, okay? Your soaps are bases. And if you ever had to like stick a bar of soap in your mouth because you had considered a potty mouth or whatever, so you probably have experienced that before, that soaps taste bitter. Let's see, and then notice that it will turn the litmus paper blue. Your aqueous solutions are also electrolytes, so your bases will also conduct electricity. And then this is similar to what we saw on the acid page, reacts with acids to produce salt and water. Okay, so that's the acid plus base, gives you salt and water. So you should make sure that you know the difference between the properties of acids and the properties of bases. So this is review on naming your acids. Remember that we have two different types of acids. We have binary acids and we have ternary acids. So let's first talk about the binary acids. So the prefix bi means how many? Two, right? So two elements together that form an acid. So remember we will use the hydro prefix and change the ending to ic. So this was an example, hydrochloric acid, which is HCl. Okay, so that is a binary acid. Once again, hydro prefix, change the ending to ic. Then let's talk about the ternary acids. So remember, ternary acids contain a polyatomic ion. All right, no hydro prefix. and we change the endings, right? Remember, 8 turns to ick, 8 to ick, ite to us. If it ends in ite, turns to OUS. So the example here for the nitric acid, notice there's no hydro prefix, so that's how I know it comes from a polyatomic ion. So that's HNO3. Okay, then if it was nitrite, okay, nitrite, then that would be HNO2, okay, to give me nitrous acid. So remember, ite to us, acid. Okay, so this one ended in 8. So this one came from, this is nitrate. The NO3, let's just kind of circle that portion there. Okay, and that's the nitrates. Remember, if it ends in 8, it ate one more oxygen, so it has one extra oxygen in its chemical formula. Now we're going to talk more about the chemical reactions of acids when they are in water. Okay, so here's a picture of what the reaction might look like. So let's say this is over here like HX, some type of acid, plus H2O. Okay? And then hydronium, you guys learned about hydronium when you were supposed to memorize your polyatomic ions. It's H3O plus. Okay, and then therefore this is the X minus. Okay, so you can see what happens here in this chemical reaction when you write out the acid with it being combined with water. So then the hydrogen comes here. Okay, so the hydrogen combines with the H2O, and that's how you make hydronium. Okay, and then you can see then the X kind of gets kicked out, and then it's like all by itself there. All right, so it's asking you, what is the source of the hydronium ion? Okay, so the source of the hydronium ion, so kind of like water is the base of it, right? And then you have the H from the acid being combined with it. Okay, and that's how you get the hydronium. And then, what is the net charge of an aqueous acid solution? So net charge means overall. So what is the overall charge on an aqueous acid solution? Well, here is a plus here, and there's a minus there. So overall, what does that equal? It's neutral, right? No charge. Okay? Now we're going to talk about acids when they are dissolved in water and when the water molecules react with each other. So remember, in order for a reaction to take place, particles will collide and hit each other. So that means since these acids are dissolved in water, the water molecules can therefore collide and hit each other and then therefore react. So this is what we call self-ionization. That is when we have two water molecules reacting with each other. And so here we have H2O with H2O. Okay, so this is showing two water molecules, okay, reacting with one another. Another way that we can write the water equation, we can write it as HOH. And the reason why I'm writing it here as HOH is so you can see how these products are formed, okay? So here we have water. That means it's going to combine with one of these H's, right? And then that's how we get hydronium, H3O+. And then notice what we have left, OH. Okay, and that's how the hydroxide there gets kind of like what I say, gets kind of kicked out right there. Okay, so two water molecules react. So two water molecules reacting, producing hydronium and hydroxide. Now, this is a very limited reaction. That means that it does not happen to a very large extent. It happens to a very, very small extent. And that's why we use a double-headed arrow to represent that it happens to a very small extent. Okay, so now let's see. This says at 25 degrees Celsius, the hydrogen ion concentration is, and then it also wants us to write down what the hydroxide ion concentration is. Also, let me note here the H3O plus hydronium is equivalent to H plus. Okay, those two ions are equivalent to one another. All right, so 25 degrees Celsius, that basically means at room temperature. All right, at room temperature, what is the hydrogen ion concentration, and then what is the hydroxide ion concentration? All right, so the hydrogen ion concentration is going to be 1 times 10 to the negative 7 molarity. And then your hydroxide concentration is the exact same thing, okay? And notice here that the H3O plus and the hydroxide, they separate into a 1-to-1 ratio. Okay, so those two are going to be equal. Those concentrations will be the same. And we also know that too because we know that water is neutral. And we'll talk more about that in the next slide. Okay, so this is just a picture showing that same water reaction, the self-ionization, two water molecules reacting. It's just showing you in molecular form with the molecules what that looks like. Okay, don't forget hydronium is H3O plus and hydroxide is OH minus. Okay, so since we had the double-headed arrow for the self-ionization of water, that means that we can write an equilibrium expression regarding that. So that is what the letter K here is, the large K, the capital K. This is for the equilibrium constant, and then the little w is for water. Okay, so this is the equation right here, and this will need to be memorized. Kw equals H plus times OH minus. Okay? And the reason why, so if you go back and you looked at your self-ionization reaction, remember when you write out your K expression, we write products over reactants, okay? So notice that these here were on the product side. Remember, H plus is the same thing as H3O plus, okay? They are equivalent to each other. So those were found on your product side, and then over the reactants were two water molecules. But remember, those water molecules were in the liquid state, so that we do not include solids or liquids in the equilibrium expression. So that's why it's just concentration of H plus times the concentration of OH minus. Okay? And if you remember, we said that this was 1 times 10. We said that was 1 times 10 to the negative 7. Negative 7. Okay, and then the hydroxide we also said was 1 times 10 to the negative 7. Okay, so when you multiply those together, then you get 1 times 10 to the negative 14. All right, so basically that Kw equation is H plus times OH minus, and that will always equal 1 times 10 to the negative 14. Okay? And we'll, in the next slide, we'll practice using that equation because you have some problems involving that on your worksheet. All right, so then this is also something that's important to know. You have actually both of those ions in solution, and it just depends which one is in higher concentration to determine if the solution is acidic or basic, okay? So as one increases, then the other one decreases. Okay, then if the hydroxide increases, then the H plus is going to go down. All right, so if you have more H plus in solution, that corresponds to the acid part of the solution or the acidic part of the solution. So if you have a higher concentration of H plus, then your solution will be acidic. If you have a higher concentration of hydroxide, then your solution will be basic. And then, of course, if the two concentrations are equal to each other, then we say that the solution is neutral. All right? Okay, now let's practice calculating H plus OH minus using the Kw equation. So first we're going to take a look at number 15, and we're going to do 15C together. Okay, so the question is, using the value and equation for Kw, calculate hydroxide if H plus is, and this is basically the H plus number. All right, so I'm going to write that down here. So this is 15C. So we're going to use the Kw equation. So Kw is H plus times OH minus, right? And it equals 1 times 10 to the negative 14. All right, so we're going to plug in the numbers here. Let's see, H plus is 8.46 times 10 to the negative 2. And then we are calculating for hydroxide, so hydroxide is going to be X, right? And the Kw, that is the Kw value right there. So we'll just write that in over here. 1 times 10 to the negative 14. Okay, now we are going to solve for X. Okay, so you're going to divide by 8.46 times 10 to the negative 2, right, on both sides. So don't forget, when you see the times 10 portion here, you're going to have to use your exponent key. Okay, so now let's put this into our calculator and see what we get. So I'm actually using my calculator on my phone. All right, so let's see if I can use the exponent key here correctly. So 1 exponent negative 14. Okay, and then that's going to be divided by 8.46. Exponent key, negative 2. Okay, so then when I solve this correctly, then I'm going to get 1.18 times 10, and let me count how many times I need to move my decimal over because it did not move it into scientific notation by itself. So let's see, 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so double check my work. I got to the negative 13, and then that would be molarity. Okay, so that is just the first little section of chapter 20 for acids and bases. We will talk more about pH, how to calculate pH, and we will talk more about weak acids and strong acids. All right, but for now, I just want you to focus on knowing the differences between the properties of acids and bases, and then knowing how to use the Kw equation. All right, so I will see you later. Bye.